Let's back up here a little bit and do a comparison with spin and orbital. Spin is what? Spin is intrinsic angular momentum. L is orbital angular momentum. Neither one of these involves a electron rotating around something, and that might surprise you. You probably thought, oh, on the orbitals it's rotating around and that gives it the angular momentum. No, that's not the case. So wipe that picture from your mind. Look at this. The commutation operators for spin look like this. The commutation operators for orbital angular momentum look like this. See the similarity? The spin operator involves x, y, and z components, and the L operator involves x, y, and z components. S squared, which we can use to calculate the magnitude, is the square of each of these operators. Same thing over here. If we take the operator of z on the z-axis, remember there are x, y, and z axes for the spin, then we get h bar over 2. If we take the L operator, then we get minus h bar r cross product with the Laplacian. So that's not quite as easy to see the exact tie-in, but it's the same kind of operation. Here our state function or state vector is a 2-valued for 1 electron, spin 1/2. And the spin is purely abstract. No spatial components are required. Over here we have a state vector which is a wave function. Each value of this is a different wave function. And this angular momentum depends on spatial coordinates. Spatial coordinates of what? Well, it depends how that orbital forms around the atom. It requires spherical asymmetry to have any angular momentum. And this exists without spherical asymmetry. So this doesn't involve the spatial stuff at all. This requires something different about the space. That asymmetry is going to show up as a magnetic moment for the orbitals, which is calculated this way. And there's the L for the magnitude of the angular momentum, which if it's just a 1s orbital, that's going to be 0. So there's no magnetic moment that's found. The spin orbital has a magnetic moment that results, which was proved by the Stern-Gerlach beam splitting thing with the magnets. And this has a correction factor here, but look how close it is. E over 2me, E over 2me. And here's the spin value, whether it's 1/2 or 1 or 0, so on. This exists without spherical asymmetry, so we can use these silver atoms, which just has an outer S shell, and this will not show up any of the orbital angular momentum. Contrary to if we take an hydrogen atom and excite the energy level to where we bump one of the electrons into the p orbital. Well, there's only one electron, so let's just say bump it into the 2p orbital, then it will show orbital angular momentum. Actually, a total angular momentum that involves the spin and the p orbital shape, which is spherical asymmetric. Another one that's probably a little bit experimentally more possible is to use the sodium and excite the atom into the 3p, excite the electron into the 3p orbital. And it's more fun down here. Let's go over spin, which we should know something about. Spin can be 1/2, 1, 3/2, 2, 5/2, and so on. If spin is 1/2, it can project as a -1/2 or a +1/2. If spin is 1, then it can project as a -1, 0, or 1. If the spin is 3/2, then you can come up with 4 different states, and if the spin is 2, you can come up with 5 different states. Now notice I said M sub S. What we look at on the periodic table is not M sub S, but we're looking at M sub L. And angular momentum, depending on the orbital that we're talking about, can be 0, 1, 2, 3, and so on. I think 3, okay, S, P, D, F. I think 3 is about all we ever see on the periodic table. So this projection can be -1, 0, or 1. Hey, 3 orbitals, 3p orbitals. Or this projection down here, if the angular momentum is 2, then we can get -2, -1, 0, 1, and 2. Hey, there's the 5 levels of the transition metals. And finally, the F orbitals, which gets really far out there, can be -3, -2, -1, 0, 1, 2, and 3. But I want to emphasize that M is not the spin. That's the projection of the angular momentum. Let's see if we're smart enough to look at this now. Down here we've got the N, which is the principal quantum number, which, I don't know, it's kind of like the S shell starts there. Here's the angular momentum, orbital angular momentum. Now the spin has its own angular momentum, but that doesn't show up here. And then this should really be the M sub L. So let's make some predictions first. We've got 3p orbitals. We've got 1, 2, 3, 4, 5 orbitals. And then over here we've got 1, 2, 3, 4, 5, 6, 7. Okay, S block is not that big a deal because L equals 0. What we're concerned about is where we've actually had angular momentum. Let's look where the first p orbital fills in, and the first p orbital should be where L equals 1. The first element where we start to fill an orbital, we're given a clue here by the green up here, is boron. So let's see what happens to the L value. The L value goes to 1. The projection is -1, 0, 1, -1, because all we're doing is filling in that same orbital but with a different spin level, so we get to repeat this. 1 and -1, or I should say -1, 0, and 1. Now let's see about these. Where's the first place we fill one of these in? Let's try this one and see what happens. Okay, L equals 2 rather than 1. So that seems to fit a pattern. And we've got an M equals -2, so let's see if we go -2, -1, 0, 1, 2, -2, -1, 0, 1, 2. Let's see if I follow that, because we're going to replace the spin values. Okay, there's a M -1. This was -2, 0, 2, oh, look what happened. Chromium filled in 2 of these orbitals, so it jumped over to 2. It doesn't, these transition metals don't follow a nice neat pattern. So we're in copper, but it filled in a 4s over here. The fact that these things don't follow a nice orderly pattern means that there's some inter-electron stuff that's really going on, and that's what all of our quantum chemistry help with the spins and all this kind of stuff should help us out.